In this video, we will demonstrate a practical approach for integrated model-based engineering based on building and analyzing digital threads. Important stages of the overall process are developing a digital thread schema, building the thread, creating and testing queries on it, constructing a data analytics framework, and automating these analyses for ongoing project validation and management. For us, a digital thread looks something like this. There are many different models. Each of these circles represents a different model of a different aspect of the system. And within each model, there are model elements, artifacts like requirements and behaviors and simulation results. Within that model, these are connected together, and we call those intra-model connections. Intra for inside the model. But we also want to tie these separate models together, and that's what the dashed orange lines represent. We call those intermodel relations, inter for between models. Together, these comprise the digital thread. A digital thread platform becomes a single pane of glass through which all the system data can be searched, accessed, and analyzed. Each digital thread schema is unique, reflecting the objectives of the project, the digital tools available to the project team, and the organizational workflow. For this demonstration, our toolset includes Syndeia, a digital thread platform from our company Intercax, and an eclectic array of widely used engineering software tools. Syndeia supports an open digital thread, integrating engineering models from a wide variety of disciplines and software vendors. It also supports multiple data consumers, including Intercax-supplied interfaces, and third-party and user-written applications for visualization, data science, and business analytics through a single, fully documented REST API. These provide both internal and external stakeholders windows on the system model, responsive to their specific needs and access. For our example, we have chosen a digital thread schema like this, applied to an unmanned ground vehicle. Requirements in Doors Next drive system architecture in Rhapsody, decomposing to hardware in Windchill PLM, and software in GitHub ALM. Further links go to TestRail for managing the test plan, and Creo for mechanical design, with Jira logging the status of meeting requirements. This schema is not unique. The Syndeia platform supports many other tools and patterns. We can now begin to build the digital thread, initially using a Syndeia plugin client for Rhapsody. Syndeia supports two general types of persistent connections between models: reference connections between pre-existing model elements, and model transform connections, which share, compare, and update information between model repositories. For example, a CAD assembly model can generate a SysML block structure. We start by using a model transform to copy requirements from Doors to the SysML architectural model. Launching from the SysML tool, we set up the Syndeia client dashboard with the SysML model on the left and Doors on the right, then dragging and dropping a requirement specification from Doors to an empty package in SysML. Quickly, the requirements are recreated on the left, each linked back to the original repository. From the Syndeia client dashboard, we can open a requirement in its native web interface. If the master requirement is changed in Doors, Syndeia can detect the changes across the connections, prepare a difference table, and update the information to Rhapsody on request. The next step in building the digital thread might take a conceptual structure model from SysML to the Windchill repository, creating a PLM bill of materials. If I modify the SysML structure by removing a part of the 5-axis manipulator subsystem, Syndeia can again detect differences across the connections. Updating the wind chill creates a new bill of materials configuration. Where model transform is not required, Syndeia can create and persist version-sensitive reference connections between domains. Here, from SysML to a test case in TestRail. No information is shared, but the link allows quick navigation to the TestRail interface. As the digital thread is constructed, we can begin to view and analyze it, here using the Syndeia web dashboard. We can view the contents of the federated repositories and interactively trace the connections between model elements. But we can also holistically analyze the thread using efficient graph database technology. Here we are using a Gremlin pattern matching query to extract all connection patterns from doors to Rhapsody in a specific digital thread, visualized, tabulated, or simply counted. The pattern, doors requirement to Rhapsody block to windchill part, traverses 3 models and includes a SysML satisfy relation as well as the intermodel links. This interface made it easy to develop and test individual queries, but we need to embed these in a more sophisticated analytical framework. For example, we can use a common open-source data science tool, Jupyter Notebooks, to string together multiple graph queries with Python data analysis and display libraries. The first-ordered cells in this notebook include provision for authenticating into the Syndeia Cloud repository, using, in this case, my personal credentials and the password I enter to start the session. The next cells execute some of the graph queries we have verified, such as the number of nodes in the Syndeia project. We can display the results in tabular format, here the traceability from GitHub to Rhapsody and TestRail. But we can do more than just look at the contents of the Syndeia database. Here we extract data from the Doors federated repository via the Syndeia Cloud REST API, independent of whether that data is part of the digital thread, and use the powerful plotting and analysis capabilities in Python to color code the results for review. Results are preserved for each run. The final stage is to automate these tasks and reports. For example, to run the scripts we just tested in notebook format each morning before 8 to alert relevant stakeholders of significant changes to the system model overnight. Rather than offering a single standard scheduling module, Syndeia supports digital pipeline tools from the DevOps world to program and execute the tasks and save and distribute the results. Here we have used the open-source Jenkins application with the Blue Ocean user interface. We choose a pipeline that will export and transform requirements in Doors to issues in Jira. Initiating a new run, we can follow the steps from extract from Doors, transform, and push to Jira. Viewing the shell script, we have a record of the individual actions, where the blue links are live and can take us directly to the Jira issue created. Finally, the successful run is added to the record. This process could be run periodically to update Jira when new requirements are created, without human intervention. In this video, we have demonstrated 5 stages in using digital threads for MBSE, using existing commercial and open-source software tools. To learn more about this approach, many examples are provided on our website, and our team would be happy to discuss them with you.